The cloud was shaped like an umbrella pine, with a long trunk that branched at the top. Soon ashes were falling, hot and dense. Next came pumice stones, black and scorched by fire. The buildings swayed with heavy tremors, the sky turned blacker than night. Then flames and sulfur fumes sent everyone into flight. Daylight came 3 days later. So writes Pliny the Younger, reflecting upon the eruptions of Mount Vesuvius in Pompeii, Italy, AD 79. The immediate effects of volcanic eruptions are well documented. Mudflows, earthquakes, tsunamis, fires, and many other phenomena can occur immediately following a volcanic event. What is often overlooked is the long-term effects of volcanic eruptions. Significant volcanic eruptions can impact climate, regionally and globally, for up to several years. But how? When a volcano erupts, it can release millions of tons of volcanic gases, aerosols, and ash into the atmosphere. While ash quickly falls back down to Earth, sulfur dioxide lasts much longer in the stratosphere. The sulfur dioxide will condense to form sulfate aerosols that reflect radiation from the sun back into space, thus partially insulating the lower atmosphere from solar heat. As such, the Earth's climate can cool by several degrees for several years. Researchers estimate that the average air parcel can remain in the stratosphere for up to 1.5 years or longer. That being said, it takes a significant eruption to change global or hemispheric climates by several degrees. Not every volcanic eruption will create this kind of effect, as different types of volcanoes erupt in different ways. In recent history, only a handful of eruptions have resulted in a decline in average Earth surface temperatures. In 1991, the Mount Pinatubo eruption cooled Earth's surface by as much as 1 degree Fahrenheit for over a year. As seen in this figure, volcanic aerosols increased aerosol optical depth by 10 to 100 times normal levels in the years following the eruption. In other words, the aerosols reduced incoming solar radiation significantly. But the trouble in studying these climactic responses to volcanic eruptions is that we do not have enough long-term data. However, with new climate proxies such as ice cores, tree rings, and sediment cores, scientists have been able to evaluate a longer history of impacts. Additionally, these climate proxies have helped improve climate response modeling and thus our understanding of volcanic climate forcing. Other than climate cooling, scientists suspect that volcanic eruptions can influence the hydrological cycle in patterns such as the El Niño Southern Oscillation, ENSO, and the monsoon season. In conducting my research, I found one distinct pattern. There is little consensus among scientists when it comes to volcanic climate forcing. A study based on climatic modeling has shown that El Niño development is most strongly favored in the winters 1 to 2 years following a northern or tropical eruption. As you can see in this figure, there is a significant El Niño-like warming for both tropical and northern eruptions, and no El Niño pattern for southern eruptions. But not all studies agree. A study based off climate proxies shows that model studies, like the one here, overestimates the ENSO response to a volcanic eruption. Many other studies show that there is no distinct relationship between volcanism and ENSO. But another study using proxies has found that tropical volcanic eruptions can force wet conditions in the Mediterranean but dry conditions over Europe. And yet, several other studies using both proxy and model ensembles show significant volcanic eruptions to suppress African and Asian monsoon seasons. As we can see here, scientists have found Nile summer flood heights to be an average of 22 centimeters lower in eruption years due to decreased precipitation. It is clear that there is little consensus when it comes to volcanic climate forcing. The impacts and the length of impacts are all up for debate, and that is simply because not all volcanic eruptions are created equal. Based on location and timing, they may have different effects on the climate. In fact, the recent underwater eruption of the Tonga volcano in the South Pacific Ocean blasted a significant volume of water into the stratosphere. NASA predicts that the surplus water vapor in the atmosphere could, in contrast to past volcanic eruptions, cause temporary warming, as water vapor traps heat. This eruption will provide the scientific community with invaluable data to help us further understand volcanic forcing in real time. As scientists predict that the frequency of volcanic eruptions will increase, it is important to understand how the climate, both regionally and globally, may respond to these types of events. But now for the question we have all been waiting for. Are we overdue for a supervolcano eruption? Will we descend into a deep apocalyptic volcanic winter? Simply put, no. Volcanoes are not on timers, and there will certainly be significant warning signs before an eruption of cataclysmic proportions happens. As a geologist and sci-fi fan, I too am fascinated by these apocalyptic volcanic questions, but we are far better off focusing our energies on studying how the climate will respond to future volcanic eruptions in the face of climate change. How could volcanoes influence the redistribution of Earth's most valuable resource, water?